Hello guys, you're welcome to my channel. Today we are going to cover the 13 topic as promised in the comment section. These 13 topics are those topics that you likely find in your theory section. Like I've checked for the past 10 years now, those topics are what they repeat in the theory section. Before we go into it, kindly click on the subscribe button. Please help me to reach 100,000 subscribers so that I'll be motivated to do a lot of videos that will help you academically. The subscription is free. Kindly drop your positive comment, like this video, and share within your friends. Thank you. Today we are going to start with radioactivity, and I'm going to summarize the topic, then we'll look at questions on it from the past question. Radioactivity is one of those topics that starts entering into your WAEC question as at year 2014 till date. And it usually be in question number 12. So now let's see how it goes. What is radioactivity? Let's start from there. A radioactivity is the spontaneous disintegration of the nucleus of an atom with the emission of particles such as alpha particles, beta particles, gamma particles. At times it can emit the three particles at the same time. At times it can emit just one. At times it can emit what? Two. With accomplish of what? Energy. Okay, that is what is radioactivity simply means. Now what brings about what is a radioactivity? What brings about radioactivity is as a result of what? Nucleus that are not stable. There are some nucleus that are stable and there are some nucleus that are not stable. From the first 20 elements, we have almost all the nucleus to be stable. But when you look at those elements with heavy nucleus, they have what? Unstable nucleus. In order for them to stable, they start disintegrating gradually. So as they start disintegrating gradually, they emit all these aforementioned particles. Let's quickly talk about the reaction of these particles for every nucleus. Now let's look at that. If I have an alpha particle, let's take for instance that an element X with an unstable nucleus has an atomic number Z and mass number A. Please pay attention here. If this element emits what? An alpha particle, it's going to produce another element Y, whose atomic number is going to be Z minus 2. And mass number is going to be what? A minus 4 plus helium, which is atomic number 2 and mass number 4 plus the energy released. Are we together, guys? Okay, if we are together, kindly note something. You will see that when this element X emits an alpha particles, the mass number of it decrease by what? By 4. Please pay attention to this. The mass number will decrease by what? By 4 whenever it emits an alpha particle. And the atomic number will decrease by what? By 2. So you balance this equation by adding what? Helium, because this is a nuclear what? Reaction. Is that taken now? Then the next particle is beta particles. What happens when an element emits a beta particle? If I have an element X with atomic number Z and mass number A, if this should emit what? A beta particle, what happens is that it's going to produce another element what? Y, whose atomic number will increase by 1 and the mass number will remain the same. Hence, I have to balance this by adding what? Electron. Electron has an atomic number of what? Minus 1 and mass number of what? 0. Then plus the energy release. This is to tell you that when an element emits a beta particles, what happens is that what? The atomic number will increase by 1 and the mass number will remain unchanged. Is that taken now? Okay, if that should be the case, let's go to the next one, which is the gamma particle. So if an element emits what? A gamma particle. If I have an element X that emits what? Gamma particle, the mass number is what? A, and the atomic number is what? Z. This will not change anything from the mass number and the atomic what? Number. So we have this plus what? Energy. Is that taken out? Why? Because this is an electromagnetic in what? In nature. It requires no material medium. Do we understand that now? In summary, if you have that an element emits alpha particle, what will happen to that element, guys? You can pause the video and give me an answer, okay? If that should be the case, the atomic number will reduce by what? 2. The mass number will reduce by what? 4. Then we add what? Helium to the equation in order to balance it, then plus what? The energy released. Then if it is beta particle, the atomic number will increase by 1, but the mass number will remain what? The same. Then we add what? Electron in order for the equation to balance. Then we add what? The energy released. Then for gamma particles, it will not change anything physically on that particular what? Element. Then we add the gamma, then the energy released. That is how we can what? Know or balance a nuclear equation. Is that taken now? Now, let us now look at what happened to these 3 particles on a field. When I talk about field, either electric field or magnetic field. Now, let's take for instance that this is a field like this. And I have the 3 particles, alpha, gamma, and beta, placed on this one, on this field. What happened is that there won't be any deflection for gamma. That is, gamma will not deflect. Why? Because it's electrically what? Neutral. That is the reason why it's not going to deflect. Then you are going to have your beta particle to highly deflect. Your beta particle will highly deflect. Why? Because what? It is a negative what? Charge. Are you getting it now? So this field here is made up what? A positive. It's made up of a positive charge like this. Okay? So like charge, they do what? They repel, or like charge attract. And that's why you see the beta particle that highly what? Deflects. Are we together now? Okay? If you now look at the beta particle, it's going to, the alpha particle rather, is going to slightly deflect. Are you seeing this now? Because what? It is positively what? Charged. Are we together? So this is positively charged, this is electrically neutral, and this is what? Negatively charged. Again, let's quickly recall what happened there. In a what? In a magnetic field or electric field, alpha particle will slightly what? Deflect, because it is positively what? Charged. Gamma particle would not deflect because it's electrically neutral. Beta particle will highly deflect because it is negatively what? Charged. Is that taken now? Another thing they might want to ask us that we need to know about these particles are the property of the particles. Let's start from alpha particles. What are the properties of alpha particles? So once you look at the properties of alpha particles. So when you say this is an alpha particles, number 1, they are positively charged. Positively charged. Number 2, they are helium nuclei in nature. They have what? A very high ionizing power. 4, they have a very low penetrating power. So they are slightly deflect in an electric or magnetic field. Are we together, guys? So when you talk about their properties, they are positively charged. They are helium nuclei in nature. I'm talking about the alpha particles now. They have what? High ionizing what? Power. They have low penetrating power. they are slightly deflected on a field, either magnetic field or electric field. Then when you talk about their speed, the speed of what alpha particle is about 2 times 10 raised to power 7 meter per second. And when you talk about the mass of an alpha particle, which is part of their property, it is 4 times mass of what? Mass of hydrogen. Are we together? 4 times mass of what? Hydrogen. Can we move on now? Thank you. Okay, if that should be the case, let's look at the properties of the beta particles. So when you talk about the properties of beta particles, one, they are electron nuclei in nature. And two, they are negatively charged. They are negatively charged. 3, they have weak ionizing power. 4, they have high penetrating power compared to that of what? Alpha particle. High penetrating power. Their mass, okay, let's talk about their speed. Their speed is about 99% the speed of light. The speed of light. So, and their mass is the mass of what? Electron. Is that taken out? So can we move on now? Have we seen the properties of the beta particles now? They are electron nuclei in nature. You can see when we balance the equation of an element that emits a beta particle, what balances the equation is by adding what? Electron. And when you look at it now, they are negatively charged, like we explained under the field deflection. And they have what? A weak ionizing power. They have what? High penetrating power compared to that of what? Alpha particles. And their speed is about 99% the speed of light. That is, they almost have the same speed as that of light. Hence, they are faster than that of what? Than that of alpha particle. Is that taken out? So let's look at the third one. So the third one, which is the gamma particles. Gamma particles, they are electromagnetic in nature. They are electromagnetic in nature, and two, they are electrically neutral. That is, they don't have charge, and their speed is the speed of light. That is 3 times 10 raised to power 8 meter per second. That's the speed of what? Of gamma particles. And again, they have no effect. They have no effect on electric field, or magnetic field. So do we get this now? So when you talk about their reaction on the field, it is what? 0. They don't react on the field because they are electrically what? Neutral. And they have what? They have low ionizing what? Low ionizing power, and they have what? High penetrating power. So, and this is a reason why we make use of them in sterilizer, because what? They have low ionizing power, and they have what? High penetrating what? Power. I get that. And they are what? Electrically neutral. That is why we use them in what? In sterilizers for medical stops, or your barbing salon where you find sterilizer, where they sterilize your clipper and the likes. So we make use of what? The gamma particles because of those properties. They may ask us, so we should know that now. Is that taken? So we've talked about the particles, and I believe every one of us understand it now. Okay, if that should be the case, let's quickly talk about what? The mass defect and the binding energy. Although I'm not going to look at calculation on it for now, as we move on this topic, we'll talk about that fully. But let me just quickly make mention of it. When you talk about the mass defect, we have an isotope and we have what? An element that we know the mass and its atomic number. You know, when they say isotope, isotope means what? Two elements with the same atomic number but different what? Mass number. So when you now talk about what? Mass defect is the difference between the mass of the actual atom and the isotope. That is the predicted one. Are we together? When you say mass defect simply means what? The difference between the actual mass of an atom and that of its what? Isotope. Then when you talk about the binding energy, the energy that is sufficient to break the nucleus of what? Of an atom. Do we get that now? Into its what? Into its component, that is going to split it into proton and that of what? Neutron. Is that taken now? That is binding energy, and that is what? Mass defect. Can we go on? Okay, thank you. Let's quickly move on to the next thing that we are meant to know about what? Radioactivity. When a substance continues decaying, it's going to continue decaying gradually as you expose it or you bury it under the soil. Are we together? Now let's see. Let's pay maximum attention here. If I have what? An atom, and I kept that atom either under the soil or on the soil, what happened is that this particular atom will start disintegrating gradually. Now you may be asked that at what time will this atom disintegrate to half of its original? That time is known as the half-life of that particular atom. Are we making sense now? So an half-life of an atom is the time taken for the atom to disintegrate to half of its original. I'm not going to prove any equation in this class because I'm going to make a full video on this lecture very soon. But for the sake of the WAEC students, let's quickly see what is an half-life. Okay, when you talk about the half-life of a substance, it's given as what? T sub 1 over what? 2. It can be small letter t, it can be capital letter T. And it's given as ln 2 divided by the decay constant. And when you say decay constant, this decay constant is the disintegration that happens to an atom of an element per second. That is the rate at which what an atom disintegrates per second is what they call the decay constant. For instance, if I have what? 10 biscuits and I kept it in a place. After 1 second, I went there, I made 9.5. After another 1 second, I went there, I made what? 9. After another 1 second, I went there and I get what? 8.5. It shows that the decay constant of that particular what? Biscuit is what? Is half per second. That is going to reduce by half for every second. Now the half-life of that biscuit is the time that will take the biscuits to reduce to 5. From 10 to what? 5. That is what we call half-life. And for you to determine that, we have this equation. Half-life is equals to what? Ln 2 divided by what? Lambda. Or I can say lambda, which is the decay constant, is ln 2 divided by what? Half-life. Is that taken? So this one is measured in per second and this one is measured in second. Do we get that now? Now let's now take for instance that you already know the decay constant of that biscuit that is going to reduce by half. Let me calm down with you guys now. It seems I'm rushing. Don't be offended. Let's take it easily now. I have 10 biscuits and I kept it somewhere. After 1 second, it reduced by half. It remained 9.5. I went there again after another 1 second. I found it to be remain what? To remain 9. That is, another half has reduced. I now went there another what? After 1 second again, I find it to be 8.5. That shows that the decay constant of that particular biscuit is half. Because decay constant is the rate of disintegration per second. Now, if I now keep checking my time and the biscuit now reduced to 5, the time that takes the biscuit to reduce to 5, 5 is the half of 10. That time that takes it to reduce to half is the half-life. Okay? If that should be the case, then we can now look at another case. You may be asked that if you are keeping 10 biscuits with the information you have at hand now, that the biscuit will reduce half per second. And you already know that afterwards, some time, which we call half-life, is going to become what? Half of its original. I may now ask you, you may be able to predict that what will be the time that will take the biscuit to reduce to what? 2. Calculate the time. Or I ask you that how many biscuits will remain after 2 hours? Are you getting it now? After 3 minutes, how many biscuits will remain? How can you calculate that? We have this equation to relate that information. If I have what? N equal what? N naught e raised to power of negative lambda t. This is the equation. N naught in this place means what? Initial atom, when you've not started checking time. Before I keep the biscuits, how many biscuits do I have? 10 biscuits. Before I keep that 10 biscuits, that's N naught, it's representing 10 biscuits. After the time t that they asked me to go and check, the number of biscuits that remain is N. And what? Lambda is the number of biscuits that is reducing per second. So this is the equation that we need to know. Do we understand this now? Okay? We have understand this. Now let us now talk about, there's another equation that looks like this. A equal what? A naught e to power of negative lambda t, where A naught is equals to what? N naught e raised to power of what? Negative lambda t. We have this when we are talking about amount of disintegration. As we move on, if the question requires us to use this, we'll talk about it as well. Is that taken now? Note this equation very well. There might be need for it. Okay? Another thing that we need to know is that if I take the ratio of the remaining what? Atom and the initial given what? Atom, my result is the same thing as saying 1 over 2 raised to power n, where n is the number of disintegration. That is the number of time that it has disintegrate. Is that taken now? We also make use of this as we go on. Another equation that we still need to know here is that the half-life of this substance is the same thing as saying that time t, the time that takes us to go and check, divided by what? The number of disintegration. Hence, I can say my decay constant is the same thing as saying ln 2 divided by what? T over what? N. Are we together? Or I just say that lambda, which is the decay constant, is n ln 2 divided by what? T. So when it is time to use this, we see questions that can review this as well. Is that taken now? Let's now talk about another thing that we are conversant with, and that is fission and fusion. Now, you all know what is called a fission and what is called a fusion. The whole of the equation I discussed are what we are to use under radioactivity. Remember, this class is a summary class. Okay? Now, let's look at something now. If I talk about fission and fusion. I'm talking about fission and fusion. These are what we call a nuclear reaction as well. It is called nuclear fission and this is called nuclear fusion. When you talk about nuclear fission is when something that is massive break to what? To small parts. That is, it splits to smaller parts. That is fission. But when they say fusion simply means what? When something that is small come together to form something that is big. Are we together now? Let's take for instance, let's go back to our biscuits. I have 10 biscuits, it's very large. If it splits to what? To 3 and 7, that is what? 3 and 7, they are not up to 10, isn't it? So when 10 splits to 2 like that, that is fission. But fusion, when I have what? I have 6 biscuits and I have 4 biscuits. Then those two come together to become what? 10. That is what? Fusion. Now when it now says nuclear fission simply means what? When what? An heavy nucleus, an element or an atom with an heavy nucleus splits to lighter nucleus with huge amount of what? With the release of huge amount of energy. That is nuclear what? Fission. I'll take it again. Nuclear fission is the splitting up of an heavy nucleus to a lighter nucleus with amount of what? Amount of energies which are very what? Huge. And when you talk about what? Fusion is when what? Two lighter nucleus come together to form what? An heavy nucleus. Is that taken now? I believe we understand the difference between the two now. Fission, heavy nucleus splits to what? The smaller one. And fusion, small nucleus come together to form what? A bigger one. Do we understand now? That is that about that. The last one we are going to talk about in this video before we start solving questions is the carbon dating. Okay, I would like you to pay attention to this because students are not familiar with this. And if you do, that will be in chemistry, not in physics. Okay, now let's quickly look at what they call carbon dating. Carbon dating. Carbon dating, I will not really talk much about it because we are in a summary class. Just stay tuned for video on a full lecture on radioactivity, and I know you are going to find it interesting. Now class, let's quickly look at it. When you look at the universe, there are some energy that are coming from another world, atmosphere, down to this world, down to this earth. We call them cosmic radiations. The cosmic radiation, when they collide with the nitrogen on earth, they form what we call carbon-14. That is what I can just say literally for now. I don't want to go into the history deeply. That is, when I have what? When I have neutron plus nitrogen, whose atomic number is what? 7, and the mass number is 14. Neutron is now combining with what? With nitrogen on the Earth's surface. This is as a result of the cosmic radiation colliding with what? With nitrogen on the Earth. They give birth to what we call an isotope of carbon-14. This carbon-14 is known as what? The radioactive carbon. Are we together now? Plus proton, whose mass number is 1 and atomic number is what? 1 also. This equation becomes what? Balanced like this. This reaction that we have here is called what? Radioactivity. Are we together now? This is what we call isotope of carbon. You know, when we talk about the isotope of carbon, we have what? Carbon-12, we have carbon-13, and we have carbon-14. Are we together? I'm talking about the carbon dating now. I want you to understand it very well so that you'll be able to answer any question coming under it. Because I believe the first question that WAEC will set under what carbon dating happens to be in 2017, which I'm very sure that 2020 they will repeat something of such, because it's not something that students are exposed to like that. Now let's see. We have seen how we form carbon 14 now, which we called what? A radioactive what? Carbon. When this carbon collides with oxygen, that is when carbon 14 collides with what? Oxygen. When they react together, they form what? They form carbon 14. Are you seeing this now? Carbon 14 dioxide. So this is called what? A radioactive carbon dioxide. This is what? A radioactive carbon dioxide. Radioactive carbon dioxide. This is where we are going when we are talking about carbon dating. This radioactive carbon dioxide that we have here is evenly distributed on the atmosphere. Are we together now? Easily distributed on the atmosphere. And the plants, they consume it during their photosynthesis. Are you getting it now? When photosynthesis is taking place, the plants, they absorb what? The radioactive carbon dioxide. Now, when the plants absorb it, are we together now? Then the animals, they eat what? The plants, and human being eats what? Animals. At times, the human being themselves eats the plant directly. Hence, the radioactive carbon dioxide is evenly distributed on everything on the surface of the earth. Both human being, animal, and plant will have the same amount in us. Now, this will remain constant in myself, yourself, myself. So, when you talk about this now, we have understand now that the radioactive carbon dioxide is evenly distributed in us now. Now, what is now the main usage of this word? Radioactive carbon dioxide. The reason why, or what we use the radioactive carbon dioxide for is this. Remember, the radioactive carbon dioxide in you will remain constant until you die. Because as it's decaying, you are replacing it back when you eat anything, animal or plant. Now, by the time someone dies, the radioactive carbon dioxide will start decaying because the person will not have anything to eat in order to replace it back. Are we together now? Hence, if you want to know the age of something, or let's say for instance now that your dog has died now, you want to know the time that the dog died, you can use what? The carbon dating to determine that. For instance, we all don't meet Pharaoh on earth, but we read about him in the Bible. We read about him in in the Quran, and wherever we must have read about Pharaoh. Pharaoh was embalmed and is currently in the museum now, Abi. Now, when you have it in the museum, you can go there and take what? Extraction of what? Of the radioactive carbon dating that remains in his body. You will compare it to what he has when he was on the surface of the earth. When we put it into the formula that we are going to be introduced to as we go on now, then we can determine the time that he died. Are we together now? That is what we use carbon dating for, to determine the age of something that has died, in order for us to know since when he has died. Are we together now? Now, let's take a look at some WAEC questions now on this particular topic, radioactivity. Thank you guys. Let's see.